Okay, so back to diamonds. So there were two issues that came up last time, and I want to say a few words about. So one question was whether you can some kind of pro-étale descent holds true in the perfectoid spaces. And so I want to just ask the question, and I'm not sure what the answer should be, whether it's a function which takes X, a perfectoid space, or even a phenoid perfectoid, and maps it to the set of, well, again, you might either consider all perfectoid spaces or just the phenoid ones. Y over X. And the group-wide isomorphism. This is a stake for the pro-étale topology. So in other words, if you have given some X prime or pro-étale cover, and you have some Y prime over here, plus a descent datum, over X cross X prime and so on, does it descend to? To X.
Do you already know descent for morphisms?
Hmm?
Do you already know descent for morphisms?
I already know descent for morphisms.
Representable things with sheets. Right?
Yes.
Yeah.
Yes. The only remark I want to make about this is that, well, maybe two remarks. The affinoid case implies the general case. That's a small argument, it's not too difficult, but I mean for schemes, the analog, say if you replace the pro-étale topology by the étale topology, it's certainly true for affine things, but it's not true for general schemes. Like generally only get an algebraic space. But the issue is that sometimes you have 2 points in a scheme and they are not contained in one affine thing, but such a thing can't happen here. The other thing is that it's true if X is what's called W local. And I don't want to explain what this means, but you should look at this paper of Bud and myself.
What if you put some conditions in the map from Y to X?
What if I put some conditions on the web from Y to X? Yeah, then it becomes better. So later in today I will explain that if I only consider finite étale maps, for example, then gluing is okay, and also glues to something finite étale.
Wait, sorry. So is the assertion of the question that affinoid perfectoids will descend to affinoid perfectoids?
Yes. So, I mean, a priori, it's not even clear that the general case I should imply the affinoid case, because I want the glued result to be affinoid again. But that would be nice to have it. Bargov looks skeptical. Anyway. Okay, so that's a question that I don't know how to answer. And then the other question that came up was roughly the following. So if you have a morphism of perfectoid spaces, and if this is pro-étale locally on X pro-étale, what is it really? So the issue was that this notion of being pro-étale was not a priori a notion you could check locally, but actually you can describe this class of morphisms here. So So let me introduce some notation I didn't introduce last time, which I should have. So what were these profilemorphisms? So locally they were of the form which I now call a finite proitar. If you can write this BB plus as a completed direct limit. So this is filtered, completed, where the AI are all perfectoid, and the are étal over the base. Okay, and then a general profilemorphism was more locally of this form. But it's not clear that a profilemorphism between the phenoids is really of this form, for example. To resolve such issues, let me state the following proposition. So, that f from x to y be a morphism of a phenoid perfectoid spaces. And then the following are equivalent. So the first is that it is some of this form. So there exists x prime to x, which is a finite proitar in surjective. Such that the composite map to y is also a finite proitar. So that's a very strong statement. So it somehow means that you should think of this map as being also, in some sense, proitar. So it's not too far from being such a thing. But it's equivalent to something which appears extremely weak. Namely, that just for all points of the base, which correspond to some map from a phenoid field with an open bounded variation subring into y, if you consider the pullback to this point, to this point. So it's just a statement about fibers. In fact, it's enough to check this geometric fibers. So for all geometric points of rank 1 even, so some sparse COC mapping to y, this pullback proitar, which in this case of a geometric point just means that this somehow decomposes as this point times the profinite set.
So if y begins life is just a point corresponding to a field,
Yes.
field, then
Yes.
is does this property is unaffected if you ramp up the field? Like the property being aphanoid pro-atol
Yes,
over a field
yes,
is
yes,
insensitive
yes.
to
For fields, nothing changes. But
go down.
So I don't want to explain the proof because it involves some ideas that will take us too far apart. But so the idea is to follow the an argument in my paper with Bargev. That someone does a similar thing in the world of schemes. So about what we call Wheatley et al. Versus Pro et al. For schemes. So for schemes, you can define Pro et al. Morphisms essentially the same way, just omitting the completion there. And then you can also characterize which morphisms have this property. And are those morphisms which are flat and for which the diagonal is also flat.
Doesn't have any finite morphism has this property?
Any finite morphism has this property, so any finite morphism is allowed now in this business, which may be very surprising. So although some morphism might look as if it was ramified along some locus, you don't really see this. So I guess people don't believe me that this can work. So let's try to convince you in an example. So let's say the space Y downstairs is you take your a perfectoid closed disk over some perfect, so this perfectoid field character, any perfectoid field if you like. And then you take X over it to be the same thing where you extract the square root of T, say. So it's and let's say P is not 2, otherwise we have not done anything. And so this is a finite et al. Away from 0. But it appears to be ramified at 0. And so what I will actually describe to you is a Pro et al. Cover of Y such that the pullback is Pro et al., which is even stronger. So that Y prime is the following thing. I have to get this straight. So it's an inverse limit of Y and prime, where Y and prime is the following thing. So it's the, well, let me describe it on points too, so that we see the image picture. So you take a small disk around 0, and then you take all annuli from I equal to 1 up to n maybe of the log of the set of x, such that the absolute value of x to the I is at most, of pi to the I is at most x is at most pi to the I minus 1. And then at each step I'm just refining the decomposition here.
Some kind of disjoint union?
It's a disjoint union, yes.
these are in Y, right?
Yes, these are subsets. That's why I'm calling them Y, right? So these map to Y.
That's why you named them Y.
And x prime will be the pullback. Okay.
You don't need to start from I equals 0.
Uh,
No, it was 1 because it goes from.
I go to I minus 1 here.
-1 on the right.
So probably
Oh,
can
sorry,
use this
this is I
there.
minus 1.
Yeah.
Right.
So these are certainly all the étale over Y. They're étale covers, so this is some kind of pro-étale cover of my Y, and so the pullback is some pro-étale cover of my X. And so what I claim is that X prime to Y prime is actually pro-étale. And so if I complete this diagram here to Y, that was pro-étale. And so in particular, this composite map here is also pro-étale. And so this puts me into this situation there.
So the map from X to Y is not pro-étale, but it is locally pro-étale.
Yes.
So pro-étale topology on X.
Yes, or even pro-étale topology on Y. So,
Yeah.
And I mean, we only have finite pro-étale if you like. Okay, so what does this X prime to Y prime look like? So this Y prime, what are the connected components of Y prime? So for each I starting from 1 and so on, I will have a connected component, and then there is some connected component which will only consist of a 0 point. So if you want, it's a topological space, it's a set of 1, a half, a third, and so on, and union 0 as a subspace of R. And the fiber over 1 over I is the set of all X such that the absolute value is squeezed in between these guys. And the fiber over 0, well, it's this intersection of all the closed disks getting smaller and smaller, so it's just 0. Okay. And okay, so that xn prime be some this part, this joint union, and on the other parts, I equal 1 to n minus 1, equal to 1 to n. I take what I had, so this part. Product over x was over y was x. Okay. So this means, so this maps to y prime, and this is certainly finite étale, because I can check this over each connected component. And so I get a map from x prime to the inverse limit over all these xn primes. So what I'm doing is I'm only doing this finite étale cover on the outer parts of this part, but I'm as n grows, I'm realizing the correct finite état part over bigger and bigger pieces here. And then in the inverse limit, this is an isomorphism. And so you can also write this, if you like, as the inverse limit of all the pullbacks, xn prime or yn prime.
The first thing is enclosed in braces. This is all x in, not x.
X and y.
It isn't x. It isn't y. Ah.
So there I'm just taking what I have on the base, so that's of degree 1 over the base. And on the other parts I'm taking this degree 2 finite état cover.
Ah, and x prime really doesn't matter.
Well, because I'm at 0, I'm just having 0, so there I'm just getting this trivial cover anyway, and so that works out. And so this is then over y prime, pro état.
So what? So I mean, in this, if you're locally pro étal, does that mean the ramification locus has to be small or something?
No.
There are no nilpotents.
There's just no such notion as ramification.
There's no nilpotents in the theory, right?
So there's no such notion as ramification on perfectoid
I'm trying to
spaces.
struggle with this kind of forever.
So I guess the intuition of perfectoid spaces is that they're just a topological entity. So you shouldn't think of them as having any coherent structure whatsoever, really. They're just topological. And so this functor I'm trying to introduce from adic spaces, so some kind of rigid spaces, to diamonds, I tend to regard it as being roughly analogous to the functor over the complex numbers, which takes a complex analytic space and associates to it the underlying topological space. So this still sees the cohomology, so singular cohomology, etc. And so in our case, the diamond will know about the état cohomology, but it doesn't really see much more than that. And so,
How, if they really are just purely topological entities, how do we see what a how should we think of pro-étal morphism?
yeah, probably shouldn't consider this concept really, but so I guess what the sense is that if I'm always working with this kind of notion, which I'm about to define as quasi-profinite, because all the fibers are profinite, like in analogy to quasi-finite morphism, then this defines some of the same topos, and we can just always work with these quasi-profinite morphisms instead of pro-étal morphisms.
You're kind of going to throw away the...
Well, I mean, in my proof last time that the structure sheaf is a sheaf on the pro-étal topology, I was really using the definition of pro-étal. But then, using this result that the quasi-profinite morphisms define the same topos, you see that it also defines the sheaf on the quasi-profinite side. But that's something that you couldn't probably prove a priori. So it's good to have these pro-étal morphisms as some kind of intermediary to go from the étal side to all these very weird morphisms.
Oh, before you erase that, can I ask one more question?
Yes.
So this map here is surjective.
Yes.
It's not in general the same thing as being a cover for the pro-étal topology.
No, that's the same thing as being a cover because it's
Because it's affinoid pro-étal?
Yeah, yes.
Okay.
Because it's already in affinoid.
So there's no problem with this quasi-compact.
Right. So I mean, this is already quasi-compact. So, right? So this is covered by something quasi-compact.
Yeah. Okay.
So is the topology more like constructible topology than what you would expect?
Well, I mean, you should, like, if you work with compact topological spaces, then using just all surjective maps of compact topological spaces defines a nice structure of side on it. So it's subcanonical, you can glue, and so on. And so you might also consider the affinoid perfectoid spaces as topology generated by all surjective maps, and that also behaves well, actually. But it's not so clear how that would be related to the étal side, but if you have this additional profiniteness condition on the fibers, then this is somehow related still to the étal side in some way. Okay, so I will call such f quasi-profinite. And I'm taking suggestions for better names. But, yeah. That's QPF. Okay, and then there was some confusion about the exact quantifiers I want to put in my definition of diamonds. So let's go through that again. So look at the side perf of perfectoid spaces of characteristic P. This cover is generated by usual open covers plus a finite Proital maps. And or finite QPF maps. And I don't really care what I choose because it defines the same topos. So it defines the same category of sheaves on this side by this proposition. And so if F is a map of sheaves on the side, let's say F is quasi-profinite. Write this out for one time. Shit. I was only doing the finite case in this proposition, so I should be more precise here. Call F x to y quasi-profinite if it's locally on X of form. Yes, in the proposition.
So now it no longer means you have profinite fibers.
Right, I mean, it has some kind of locally profinite fibers.
Locally quasi-profinite.
Oh. That's what I mean. So say F is... Now there's a question what I should call this. Well, I still call it quasi-profinite. If for all maps from the sheaf represented by perfectoid space to G, the pullback is again representable, and the corresponding map from Y to X is quasi-profinite. And so, and finally, we have a diamond. That said, there exists a surjective quasi-profinite map from something representable to F. And so in particular, this means that if you look at the equivalence relation induced on X times X, so Hx comes over F Hx, and that this is representable. So we get R in X times X, representable equivalence relation. That's because that's a pullback of this map along from Hx again, and I'm asking all such pullbacks to be representable.
Can we discuss whether Hx is a sheaf or is it irrelevant?
Hx is a sheaf. That's what I proved last time, right?
I thought you changed the topology.
Yeah.
Well, we didn't change the topos, so being a sheaf doesn't change.
Can you comment on that a little bit? Why is changing the topology not change the topos?
Well, you can define any quasi-profinite cover by a prototype cover as a proposition. And so if you want to check, like it's enough to check always for refinements.
So X could be something like SPD, QP, no, let's try to do the example of square QP diamond.
So yeah, I'm coming to the example of square QP diamonds in this lecture again.
So this map R to X cross X is a QPF monomorphism. Can you say more than that?
Can I say more about this equivalence relation?
Or no, I'm sorry. No, I'm sorry. No,
maps
it's
to X
just
or QPF,
the map's down at QPF. Yeah.
Yeah.
But it could be rather. It doesn't have to be some kind of sub.
No.
Yeah, right. Okay, yeah. Yeah, but maybe it's
Well, yeah. So it's functorially injective, but
that's about it.
about it, I guess. Yeah. So yeah, it could be something really weird inside. So it's not somewhat given by some equations or anything in general.
But it is QPF on each file. I mean, on each copy of X.
Yes. Yes.
It's QPF on each of the two copies of X.
So to prepare my discussion of QP diamond, let me say a few words about G-torses. So let's say if G is any finite group, then we have this notion of a G-torser on any topos. And, well, what is it? I mean, it's some kind of map F to G plus an action G times F to F with some conditions such that locally on G, F is isomorphic to G cross G. And some locally meaning for a cover in this topos and so on. So we can actually, in this protal, and so actually I might replace G by any group object in this topos if I want. So well, so what I really want to do is I want to consider a profinite group, not just a finite group, because last time I wanted to divide by ZP cross, and ZP cross is just a profinite group. So for example, if G is a profinite group, so an inverse limit of G mod H, where H and G is open normal. Then we have a sheaf G, which is the inverse limit of the constant sheaves G mod H. Which is not the constant sheaf G. So if X is a phenoid, for example, then the X-valued points of this group are not just, they are the continuous maps from the underlying topological space of X to G. The point being that whenever I model out by some open normal subgroups, the induced map to the quotient will be a continuous map to a discrete set, thus corresponds to, gives you a section of this constant sheaf for this discrete group. And then a compatible system of such maps then just gives you a continuous map to G. It's not locally constant. So if you want, the point is that our perfectoid spaces, they may have a profinite set of connected components. And so it may have some non-trivial maps to some profinite groups. And so then again, a G-torsor is the same kind of thing where I replace by G underlines.
G is finite, and then G torsor and G bar torsor are the same.
Yes, so if G is finite, then this doesn't change anything because this inverse limit is reduced to a single term.
And these won't be representable in perf. They won't know object in perf.
These are not representable because there's no base point in my category, really. So there's no final object in my category.
If their perfectoid spaces over a particular perfectoid field,
yes,
then they would be representable.
Yes. So they are not themselves representable, but whenever it takes a product with something representable, it stays representable. So I mean, this would work for any profinite set. And X is a perfectoid space. Then, so with the same recipe, I can define this S underlined. And if I take the product of this with sheaf represented by this X, then this is really the sheaf represented by something we might call H, X cross S, so that's representable. And what is the result? It's just the inverse limit of the X cross Si, where S is the inverse limit of CSI.
So a G underlined torsor is the same thing as inverse limit of.
That's what I'm about to say. Yeah.
So X cross SI just means the disjoint union of copies.
And this is just somehow a disjoint union. Yeah. So that's the finite disjoint union of copies of X. So if there was a final object in the category, this would mean that S itself is representable because this functor would be somewhat trivial. But there is no final object in the category because I'm not specifying a perfectoid base field over which everything lives. Okay, and so this condition here, for example, means that locally this is relatively representable, meaning that the pullback is representable because it's just a product. But as I said previously, I don't know whether in general this implies representability after pullback to anything, but for G-torsors it's actually true. So let this be a G-torsor for some profinite group. Then for any phenoid well, maybe I should call Y. So BB plus mapping to G. The pullback HX cross Hy is, sorry, what am I writing? F times G Hy is some Hx is representable. Where X is some bar AA plus with A, say, being the completed direct limit over all H and G which are not open normal. Some AH. Whereas this AH over B is a G mod H torsor, finite italic G mod H torsor in the algebraic sense.
this mean that something like a GLN-QP bar torser is going to be the same thing as a top QP local system?
GLN QP bar is not profinite.
No, you meant underline.
Well, you can,
Well,
if
still-
you take GLN Z, you can take that just to, you can sort of
Well, I
extend
think
it
if you
to
do
maybe you weren't.
maybe. So we have. Maybe you might want to check the discussion in my paper with Bargev in the algebraic world.
Okay.
And whatever works there probably does also work here.
Okay, but you're not planning to extend this to the definition of the case where G is not locally closed.
Not today.
Can I ask about the square root example earlier?
Yes?
Is that a Z-mod 2 torser?
No, it's not a Z-mod 2 torso because over this 1 point, it's just 1 point. So
Okay, good.
Yeah.
But it is pro-etale.
it's pro-etale. But it's pro-etale with an action of Z-mod 2, but it's not a torso, right? I mean, that's
Yeah.
still as it
But
should
over
be.
there, so, yeah, okay.
Wait a minute, not Freud, right? That's-
No, it's
No, but it's after,
Yeah.
it's a sheet.
Oh, this is sheaf somewhat. Let's forget about this notion.
Describe it, you the basic.
Okay, so let me give a sketch here. So first you reduce to the case where G is finite. So how do you do this? So if you have H and G any compact open subgroup, open normal subgroup, then you can look at F divided out by the action of this group H as sheaves. This maps to G still. And this is a G mod H torser. Everything can be checked locally. Locally it's just a product, and then it's a direct check. And this F, of course, is the inverse limit of these F mod H's. And so, if we know the structure of all these F mod H's, and they are somehow represented by such AH's, then we get the result. Okay, and then the crucial statement you need is that if you look at a finite perfectoid X, or I should say Y, mapping to finite étal Y over X, that this is a stack for, well, the topology we're working on, whatever we call it. Let's do it. And so again,
So this comes down to this two-limit argument again?
yes, but here it's again good that we can check this. So we want to prove it's a stack on our side, but it's enough to check this for pro-étal covers again by this proposition. But for pro-étal covers, so that's an X on a Y. So f y prime to y prime to y is the finite pro-étal cover. Then the category of descent data finite étal descent data for y prime to y. This is just a two categorical limit over all I of the category of finite étal descent data. For these terms in the limit. That's again because of this Elki-Gabaram arrow thing. That finite étal covers over some completed direct limit are the two categorical limit of the things downstairs. And then you just have some bunch of finite extra data for which the same holds. And so if we have descent for these individual y primes over y, then all of these categories would be equivalent to finite étale x over y. And so we would get the result here. So we can reduce to étale descent. But again, this is somehow a point where it's useful to have this intermediary of the pro-étale topology. And so for étale descent, any number of arguments could work. So either you do another such argument to reduce to the case where everything is Noetherian. Case and
Of hex spaces or what?
yes, Noetherian spaces. I mean, so the kind of space is considered by Huber, and use the result of Huber. That there you have such a thing. Or another thing you can do is there's an argument of de Jong van der Put. That in general, étale descent follows from some descent on the underlying topological space, so what's maybe called analytic descent, which in our case is given by the result of Kedlaya and Diu. Or for perfected spaces, it's already in my paper. Analytic descent and finite étale descent. So you can reduce to those two cases individually. And finite étale descent is somehow okay by the usual flat descent. As an algebraic topology, as an algebraic geometry.
Of course, even to prove that, you use the two-limit argument, didn't you? Like to show
No,
that-
I mean, what de Jong and van der Put shows that if you have a pre-sheaf on the
No,
étale
but
topology,
the point is the finite étale descent is because maps between, a finite étale coverage of an affinoid perfectoid are just given by algebras, but that came from the,
you mean this
somehow-
step already uses.
well,
yeah.
the bottom is set. Or so
Yeah,
it's, has the-
I mean, so
Have the two
what I'm
remaining.
even proving is that somehow if I, well, this guy is also a phenoid. Oh. So
yeah.
by your results, I'm just asking it locally is the same as asking it globally. That this is also a phenoid. And then if I'm already asking it's a phenoid, it's really usual flat descent. So this reduction argument of de Jong van der Put is a bit involved, but it uses some of that, contrary to schemes, for p-adic spaces, étale morphisms are somewhat generated by usual open emergence and finite étale morphisms.
When you write this directly with A,
Yes.
A sub A, if A selects the point,
A sub, I don't know, it's not clear. Yes, no, sorry, yes it is, yes. AH is really the, yes. A lower H is really A upper H. Yeah. Okay, so back to QP. So last time I was giving this. So in order to keep my notation a bit more compact, whenever I just write spar of some ring R, I mean the spar of R in the spar bonded elements. And maybe I should have introduced this notation before. So I was defining this diamond associated to QP, spar diamond QP, as being the one associated to the cyclotomic extension and then divided by the action of CP cross. And really I should be underlining this because I'm regarding this as a profinite group. And so let's completely unravel this. So the diamond for some perfectoid space I was defining as the sheaf represented by its tilt. So you have the sheaf represented by QP cyclotomic tilt, where I can identify the tilt with this kind of perfect wrong series field, where, by the way, the action of CP cross on here gives you an action here, which is the action which sends t to 1 plus t to the gamma minus 1. And so that gadget here comes equipped with an action of ZP cross, and so what you do is you take the co-equalizer for two maps. There, one is just a projection, and one is the other is the action. Okay. And so what I would like to know is that the obvious map from the diamond for QP cyclotomic down to the diamond for QP, that this is actually a ZP cross tools. And actually there's something to show. So, like, if it would be the case that the ZP cross action on here is trivial, I wouldn't dividing out by anything here. And so this thing would just stay the same as QP cyclotomic. And so this would just be the identity. So I need to know that the ZP cross action on here is really sufficiently non-trivial. So. And so the precise statement you need is that so you have a map from that guy to the fiber product let's give this map some name, say G. That is a nice morphism.
Where it's those two maps in the co-equalizer are the ones you.
Yes, so one map to here is the projection, and the other map to here is the action. And I made them equal as maps downstairs. Okay. So let's do a proof. So
is this? I mean, in general, you could just have some profinite Galois extension. It's something specialized, basically.
no, there's nothing special here. So really, the correct setup to do this in, but where notation becomes, where it's just much more notation, is where you have any similar part of QP algebra. You pick a tower of finite total extensions whose limit is perfectoid, whose completed limit is perfectoid, and then you do the same thing where you replace QP cyclotomic by this completed direct limit of these finite total extensions, divide out by this Gabor group of this extension. And everything I'm about to say works in this generality, and that's something I want to mention next time. Except that I'm cheating this proof by, but okay. So in general, you have to do the proof slightly differently, but anyway. So, namely, the following statement might not be enough in general. So certainly the action map from ZP cross to the automorphisms of this field. That's injective. In fact, the better statement you should use is that ZP cross acts freely on geometric points. What's this field? Which is a thing that will be verified and will be true in general. But, okay. Okay, so we certainly have this map G here, and we want to construct some inverse. So this injectivity is pretty clear by this formula. But, okay, so how do we construct the inverse of 2G? So we certainly have a map to this one factor here, just because so this map to here was just a projection, and so if we further project to this factor, we somehow recover this factor. So we need to recover the other factor. So we need a map to ZP cross. And so we can do this locally. So if we somehow construct something canonical. And so locally, a map into this product really means I'm having two maps here, which are really maps from QP cyclotomic. Well, so if I have F1 and F2 from QP cyclotomic to my ring R, such that they agree when I consider them as maps down to spot QP, spot diamond QP.
On the diamonds, on the tilt side?
Sorry, I should tilt this. Yes, thank you. And so this means that they, one brings one to another by the action of CP cross. But so what this means is that there exists gamma, which is not just an element of ZP, but it's really a continuous map from the p-adic spectrum of R. Such that F1 of T is, sorry. So okay. So let's take an R plus value point. Of the fiber product. So this means that we have two maps from the tilt, which agree as maps downstairs. And so this means that the associated maps down here are the same. And so this means that after some pro-tau cover, some of the difference is given by what we're co-equalizing here. So such that there exists R to R tilde some finite pro-tau cover. Let's write this the other way. And some gamma there, it's called gamma tilde. Should have followed my notes from the start. Continuous map, which conjugates one to another. Tilde minus 1. It's not. And I leave it to you as an exercise to define what this means. So, for example, you can evaluate it on any point, and then this equality is just a pointless equality if you like. But actually, you can define an element of R tilde a priori, which gives the correct value at each point. And so, really, what we want to have is a map from the adic spectrum of R plus down to ZP cross. So, we want to show that gamma factors over the adic spectrum of R plus.
Gamma tilde factors.
Gamma tilde factors over some gamma, thank you. Which is still a continuous map.
That the map from the ZP cross times spec Q cyclotomic inject into the fiber to the product. Is that correct? Yes, but if you have a group action on a sheaf and you want to take a quotient with the map to the product is the monomorphism, doesn't it follow that the sheaf quotient is the torsion?
Well, if you're not saying I'm proving something weaker than what I need, I'm still satisfied. So you're saying that it's a priori clear that G is surjective, or?
Well, I could be completely wrong.
Yeah, it's probably right.
But you define this, the diamond of QP as being a sheaf co-equalizer, right?
Yeah, so I guess it's clear that it's surjective, yes.
Yeah.
Yes. But yeah, I need to prove injectivity. Okay. For that, it's good enough that it's constructed one-sided inverse. Well, okay, maybe the way you're arguing is actually better, but anyway. It's an easy topological argument to show that it's enough for this to show this constant no fibers. So this way I could factor it over a map, and to check continuity, you can check over this cover. And so this means that I can assume that this field and then also
fibers of tilde to without tilde.
Well, I can even assume it's an algebraic contrast. Give me the field. Look at a geometric point. And so then this R tilde will just be some profinite set over it. So in particular, it has all the points as sections. And so, if not constant, we have two different sections. And so two different elements such that f1 of t is 1 plus 2 of t to the gamma I minus 1 in C for 0 and 1. In other words, f2 composed with gamma 1 is equal to f2 composed with gamma 1 from this Laurent series field to C. And so this map is necessarily injective, so this would mean that the action is the same, but then because of this, we get that the elements are the same. And so in general, if I have a general kind of ring here, this map would not necessarily be injective, and so the correct statement to have is that the action on geometric points is injective. And so now we really get the corollary, what we want, that this map down to spar QP is a ZP cross torsor. Why is that? That's because it is after pullback along the surjective map. Okay. And so once you know this, you can also verify this remark I made last time, that you can actually describe what points of spar of QP diamond are. So if you take the R plus value points of this guy, that's the following stuff. So first of all, if you have such a point, you can pull back the CP cross torsor along this map, and I proved that all of those are really representable in a simple way. So that gives you an R to R tilde from the CP cross torsor, meaning that it's this completed direct limit of C mod P to the NZ cross torsors. And then over it, you have a map from QP cyclotomic to this guy, which corresponds to as a map. And this map actually has to be ZP cross equivariant, because it somehow comes via pullback from QP cyclotomic flat to R tilde. And you consider such guys and so you can also say what it means to give such a ZP cross equivariant map. It's just a topologically nilpotent element in R tilde, which is the image of this T, such that ZP cross acts in a specific way on T.
So R plus didn't play a role.
So R plus didn't play a role.
I mean, this map has to carry everything of it.
Well, so implicitly, one has to ensure that FP power series in T map into R tilde plus, but that's actually automatic, because the constants certainly map into R tilde plus, and all the other elements are topologically nilpotent, so they also map into that.
So like R tilde also plus to plus.
Yeah, so I would have to include this other ring here as well, but that's no issue.
But I guess the point is that once you know, if you change what the plus was, that wouldn't change the category of the
ZP cross torsors, yes, because there's a more algebraically described phrase. So ZP cross torsor was the same thing as this finite talk Z mod P to the n Z cross torsors of R, and then complete directly. Great. So, and so now finally I can come to this long promised theorem that the factored spaces of a QP are isomorphic. It's category of such to perfectoid spaces X of characteristic P plus some kind of structure morphism. X diamond to spiny QP. Where I'm again using this notation that X diamond is the same thing as a functor represented by X.
Is there any condition on that morphism, or is it just a morphism of diamonds?
It's just a morphism of diamonds, meaning morphism of sheaves, yeah.
You wrote a superscript U.
Yeah, what is that?
It's a diamond. SBD, QP.
That's a straight mark on the board.
Oh,
No. They're,
Let them out.
quotation.
I call this.
Quotation. Okay.
You could erase that.
Yeah, quotation.
That's why I would.
So in this sense, I was a functor which takes a perfectoid space and associates to it the tilde precisely forgets the structure morphism. Calls the space left over QP. So what is the corresponding statement on the phenoids? Is that if I evaluate bar diamond QP on some perfectoid characteristic P thing, then this precisely parameterizes untilts of this guy to characteristic 0. So it's a set of sharp perfectoid QP algebra. Plus an identification of its tilde with R. And those two are pretty clearly the same statement. Okay. So, and of course to verify this, we want to use this description of spotty QP there. And so we need to define functors both ways. So I think there's both functors are not completely obvious. So one functor is the following. So which direction does it go? I start this direction. So if I have R sharp of perfectoid QP algebra, plus an identification if it's tilde with R, then so to produce a point of bar diamond QP, the first thing I have to produce is a ZP cross torsor. But that's easy on this side, because there I'm just kind of just cyclotomic extension of QP, which I can tensor on it. So let R sharp tilde be the correctly completed tensor product with cyclotomic. Meaning it takes a direct limit of the ones where you adjoin just the p to the nth root of unity and then complete. And so these are finite algebra are sharp, and by almost purity this means that they are themselves perfectoid algebras, and so we are not leaving the world of perfectoid algebras here. So that's some kind of ZP cross torsor over R sharp. And so if I tilt, then this guide sharp over R is now still a ZP cross torsor. And it comes with a map from QP cyclotomic tilt by the functoriality of the tilt plus. And it's certainly ZP cross equivariant. Two. Okay. And so we need to construct the inverse. So now we have given a point of spar diamond QP. So in other words, we have some ZP cross torsor and ZP cross equivariant map. The tilde of QP to our tilde. And we need to produce some until to characteristic 0 of R. But let's try our tilde first, but here it's easy because if I have some perfectoid base ring, for example, QP cyclotomic, then tilting is an equivalence of categories on one side on the other. So this means that we get a canonical untilt R tilde sharp, which counts with a structure morphism from QP cyclotomic.
With the action. With the action, with ZP star and everything.
Yes. Still has a ZP storage. But of course, the ZP storage is not as a QP cyclotomic algebra, but it also acts on QP cyclotomic. And so then, of course, we do what we have to do. We let R sharp be tilde sharp takes invariance. And we have to show that this is actually big enough. So that's because of the following lemma. That if I look at the continuous group cohomology, CP cross acting on this plus subring of it modulo pi sharp for some informalizer pi sharp. So here I take pi and R, pseudo uniformizer, such that pi sharp to the p divides p in tilde sharp. I can always find such a guy because if I pick any, then because p is topologically nilpotent, some power of p will be divisible by this. But then if I take a sufficient p power root of it, that's okay.
R tilde sharp plus?
Well, so as I said, I can also canonically untilt the integral subrings. There are some conjecture. And so this is actually almost the same as
Yeah, that is that division happens in R tilde sharp servers.
Division happens.
Well, when you say so something, one element divides another on the right-hand side of the board.
Better? And 0 for bigger than 0. So this means that mod pi sharp, I get big invariants, and I also have no obstructions to lifting. So this means that all the invariants will also lift.
Is that R sharp plus that you're using?
There's no R sharp yet. R is this.
Oh,
R.
okay.
At the end of the day, that will be.
And at the end of the day, that will be R sharp plus mod pi sharp. And so what's the proof? This here we can identify under tilting, so it's a continuous group cohomology of CP cross on R tilde plus mod pi. And then we can use pro-étale descent for the structure sheaf O plus mod pi almost on the pro-étale side, or along this map R to R tilde. Something I proved last time implicitly is that the scar here is a sheaf on the pro-étale side and the side cohomology groups vanish, which implies exactly this behavior here. And so, if you know that, then we get that with these invariants, we still have that they are big enough. So in particular, mod pi sharp, they will be the same as R plus mod pi then. And so this means that R sharp isn't flat itself. Because the tilde is formed from this by passing towards the inverse limit of Frobenius and so on.
Peter, is it formal that this equivalence up here preserves the continuity of the action of ZP star, or do you have to look at the construction?
Well, it certainly acts continuously here, right? Because it's the same as here.
Ah.
Yeah, maybe you have to go to the construction, but somehow all these things are. Yeah. Explicit. Okay. Yes?
So, to sort of diamondify an p-adic space, you want to take it perfectly covered and tilt and then do the
Yes, so actually it's something that one can prove is canonical now. So a priori somehow this bar diamond QP there, this depended somehow on the choice of the cyclotomic tower. But now I'm giving a description of what points of it are, which somehow doesn't refer anymore to the cyclotomic tower. And so this shows it's independent of this choice. And so in general somehow the same argument works.
in general for any x that I pro-étale.
I mean, as I said, you can choose find this tower, find the tower covers whose limit is perfectoid, and then you can do this construction. And then in general, you can show that again, this somehow parameterizes perfectoid spaces together with a map to this algebra you started with, and which shows that this is somehow canonical, and then you can do and so on. Well, I'll say this next time. Yeah.